Hello, today we're continuing in our series of GCSE physics revision looking at electromagnetic waves, or as we shall see, that includes light. So light is an electromagnetic wave, but it is only part of what is called the electromagnetic spectrum. So let's put light, visible light, the light that you can see, is part of the electromagnetic spectrum. And light, of course, as we know, has colours which range from the rainbow of red all the way up to violet. The full colours, of course, are red, orange, yellow, green, blue, indigo, violet, and those are all the component colours of visible light. That's what you can actually see. But that's just a small part of what is going to be a full electromagnetic spectrum, which has got 7 elements in it, of which visible light is one. If we go beyond the red, we get to what's called infrared. And the difference between infrared and visible light is that infrared has a longer wavelength. In other words, as I move in this direction, the wavelength lambda is increasing. So infrared, longer wavelength than visible light. If I go beyond infrared, I get into a new region of the electromagnetic spectrum, which is called microwaves. They too are electromagnetic spectrum, but they have longer wavelength. And if I go even further, I shall get into a section which is called radio waves, even longer wavelength. Now let's suppose I go back the other way. I've gone beyond the violet, so I get into the region that is beyond the violet, and that is ultraviolet. And now I'm going, of course, to shorter wavelengths, because wavelength is increasing in this direction, so as I go in the opposite direction, wavelength is getting shorter. When I get past the ultraviolet region, I get into what are called X-rays, and if I go further still, I get into the region which is called gamma rays. Gamma rays come out of nuclear reactions. All parts of the electromagnetic spectrum travel at the speed of light. The speed of light is 3 × 10⁸ meters per second in vacuum or in air. But of course, as we've seen, it goes much slower in other transparent media. So since we know, we've learnt this before, that the speed of a wave is equal to its wavelength times its frequency, if that speed c is constant at 3 × 10⁸ meters per second, what that means is that if the wavelength increases, then in order to keep c constant, the frequency must decrease, such that the product of the two always comes up to the constant of c. So as wavelength increases, frequency decreases. So this graph, which shows increasing wavelength to the right, is also increasing frequency to the left. So at this end of the spectrum, we've got high wavelength, low frequency, and at this end we've got low wavelength, high frequency. Now it turns out that the energy of a wave is generally proportional to its frequency. The higher frequency, the higher energy. And in general, you can say, the more dangerous that wave might be. So the higher frequency waves are also the more dangerous waves. And that's why gamma rays, X-rays and ultraviolet are dangerous compared with all the remainder. Though, as we shall see, there is danger in pretty much all of them. The sun emits pretty much all radiation in the electromagnetic spectrum. We principally see its light, so we see the visible light. We feel its heat. That's infrared. Infrared is essentially radiated heat. We're not conscious of microwaves and radio waves because there's nothing about our personal being that easily acknowledges them. We will be aware that some ultraviolet gets through to us, though a lot of it is thankfully absorbed in the atmosphere, but some of it gets through because that's what causes our skin to tan and possibly to burn. Thankfully, any X-rays and gamma rays which are emitted from the sun are absorbed by the atmosphere. So they keep it, otherwise we would in real trouble, wouldn't we, if we went outside and were exposed to heavy doses of X-rays and gamma rays. So let's now talk about how we use these different elements of the electromagnetic spectrum, what their properties are and why we would use them the way we do. And we'll start at the far end, the high wavelength, low frequency radio waves. Radio waves can be anything from about 1 metre to 10,000 metres in wavelength. So long wavelength. And in fact, in the days when we used the electromagnetic spectrum in that region, the radio waves were divided into 3 categories: long wave, medium wave and short wave. Long wave, well, in the old days BBC Radio 4 was transmitted on long wave 1,500 metres. That's about a mile. So the waves that were emitted from the transmitters had a wavelength of 1,500 metres, about a mile. That's long wave. Medium wave was typically something of the order of 300 metres. Short wave, very much shorter than that. Now, the behaviour of those waves determines why you might want to use them. For example, long waves, which have a wavelength of a mile, will diffract. Remember what diffraction is? Diffraction is when you're going past obstacles. Do you notice them or not? Long waves will travel round the surface of the Earth. This is the Earth. Here's a long wave transmitter. Those long waves will travel. It doesn't really matter if there's a hill or a mountain in the way, because they have a wavelength of a mile. They will just bend round those mountains. And indeed, some medium wave can do the same. So one advantage of long wave is you can send the signal over very long distances. Unfortunately, one of the disadvantages is that the quality of that signal may fail or may get worse. So it's not necessarily the best way of transmitting information like radio signals. Now, before I tell you about short waves, I need to tell you about something which exists high up in the atmosphere above the Earth. It's called the ionosphere. And what it is that ultraviolet light from the sun hits atoms in this high region of space or above the Earth, and that ultraviolet light has enough energy that it can kick electrons out of atoms. And in that way the ultraviolet is absorbed, and that's one of the ways that that the atmosphere protects us from ultraviolet radiation. So high energy ultraviolet light comes in, that energy goes into an atom, kicks an electron out, so you've got free electrons and you've got positively charged atoms, because as we've seen before, if you take an electron away from a neutral atom, you're left with a positively charged atom. And so you've got the process of kicking electrons out is called ionization, and if you ionize this part of the atmosphere, that is called the ionosphere. It's got a lot of positive and negative charges floating around in it. And what that means is, since we're talking about the electromagnetic spectrum, and it does what it says on the tin, it's got an electric element and it's got a magnetic element on it, you would expect that if the electric element encounters charged particles, then something might happen. And that's exactly what you get with short waves. In fact, I'll draw it as a separate diagram. Here is the Earth. Here is the, as it were, the surface of the ionosphere. The ionosphere is out here. All the charged particles. Short waves reflect off of the ionosphere, reflect off the Earth, reflect off the ionosphere, reflect off the Earth. So short waves can progress around the world by bouncing back and forth between the Earth and the ionosphere. But I'm afraid that although this is very handy, these long waves, whether they are, these radio waves, whether they're long wave, medium wave or short wave, for varying reasons you can whiz them round the Earth. The slight deficiency is that the quality of the signal that they carry can become distorted. Consequently, radio and television signals these days have trespassed into the next region up of the electromagnetic spectrum, which was the microwave region. So these are much shorter wavelengths, but the trouble is that much shorter wavelengths will not diffract around mountains. Consequently, if you want to send microwaves from a television transmitter to your house with a television aerial, then it pretty much has to be line of sight. If there's something in the way, then those microwaves will not go round it. And you can use microwaves two ways. You can either have a terrestrial transmitter, one situated on the ground, or of course you can have, here's the Earth, here's your house, and here up in space is a satellite. And that satellite can transmit microwaves, and you receive those in a dish aerial. But the dish must of course point precisely towards the satellite, because the microwaves are not going to go round anything, so there has to be a line of sight. Furthermore, this satellite, obviously, which is orbiting the Earth, must always be relatively in the same position to your house, otherwise you'd constantly be having to move the dish. And we call that a geostationary satellite. What we mean is that the satellite orbits the Earth at the same speed as the Earth itself rotates. So from the point of view of observing, it seems as though the satellite is always in the same position above the Earth, because the Earth rotates, the satellite rotates, but they both rotate at the same angular speed, which means they both do one complete revolution in 24 hours. So it looks as though the satellite is always in the same place, so you don't have to keep adjusting your aerial. Incidentally, the satellite has to be about 22,000 miles above the surface of the Earth in order for it to be geostationary. You'll find out why that is the case when you do A-level physics. So far so good. The quality of the signal that is carried in microwaves is much better than in the longer waves. There is the disadvantage that you must be in line of sight. There are two types of region that are used for these waves, UHF and VHF, which stand respectively for ultra high frequency and very high frequency. The ultra high frequency tend to be the frequencies used for television. The very high frequency are the ones that are used for radio. Of course, we now tend to do a lot of digital transmission, but when we were still doing frequency modulated, then these were the regions that we used. But as we shall see in a moment, that there is another potential disadvantage to using these microwave region waves for television and radio transmission. And that brings us on to the next property of a microwave, which is that if you pass a microwave through a potato, what happens is that the energy of the microwave is absorbed in the potato, and specifically it is absorbed in the water molecules in the potato. Water molecules will absorb microwaves of a particular wavelength, and in doing so, having absorbed the microwave, the energy of that microwave has to be converted to something. It's converted to heat. And consequently, all the water droplets in the potato, or indeed anything else that you may put in your microwave oven, all the water droplets absorb microwave energy and are heated up to boiling point, of course, and they effectively cook the material from the inside. So you're no longer providing heat on the outside, but microwaves penetrate the food, they get absorbed by the water molecules. The water molecules therefore heat up because that's the heat energy, and that cooks the food. This is good for the purposes of a quick way of cooking food. But now let's go back to our radio and television transmission and ask ourselves the question, suppose it's raining. What do microwaves do when they hit water? they are absorbed and the water heats up. Well, that's not going to have much effect on rain. It'll have a marginal effect in terms of heating up the rain. But what it will do, what that rain will do, is to absorb some of the microwaves. So in a heavy rainstorm, you may well find that your television or radio reception is poor because some of the signal is being absorbed by the rain. So now we move up the spectrum. We've done radio waves and microwaves. The next is infrared. Infrared is essentially what we perceive as heat. Not all heat comes to us through infrared radiation. As we shall learn later, there are three main ways in which heat is transmitted: by conduction, by convection, and by radiation. The conduction, you pretty much touch a radiator and it's hot. That's conduction. Convection is the air above the radiator circulates. That's convection. Radiation is when heat from the sun arrives, having travelled through 93 million miles of space. That's radiation. That's infrared. So infrared is a way of keeping us warm. You can have an infrared heater, which essentially is just emitting infrared rays, which are warm. But infrared is used in a variety of other ways. It's used to send signals. For example, almost certainly the remote control of your television set works on the principle of infrared radiation. Infrared signals are sent to the television box to save you having to get up and adjust the television, and the signals are coded inside the infrared so that, for example, one code might be switch the television on, another code might be change channel, another code might be increase or decrease the volume. So infrared is very popular for television remote controls. Infrared is also used as a security device. You have an infrared detector. When it's dark, you can't see any visible light, but of course if anybody comes close, that body will have body heat. That heat will be radiated in infrared, and that infrared radiation strikes the infrared detector and sets off the alarm. And so that's the way infrared detectors work, by detecting heat which suddenly appears on a cold night. A body comes by, an ordinary person walks by, they have body heat, that's infrared radiated, and that is detected. Infrared can also be used in a camera. Again, instead of seeing ordinary light on a very dark night when that picture would be entirely black because there's no light, infrared will pick out a fox running past. Usually the background is black and the fox is white, because the hotter something is, the whiter it is. So when you've got a dark, cold night, that's black, and then a fox that has body heat runs past, you see the white effects. That is all done by infrared technology. The next region is visible light, which I'm not going to dwell on, because in many senses, although visible light occupies only a very small part of the electromagnetic spectrum, and light in the visible region has a wavelength of approximately 10 to the minus 7 meters. So when you think that long wave was 1500 meters and you were getting down to microwaves, which are maybe a few centimeters, by the time you've got to visible light, you're very much smaller wavelength and therefore very much higher frequency, and the wavelength is about 10 to the minus 7 meters. And it's a very small part of the electromagnetic spectrum, but of course to us humans it's a critical part, because that is the thing that we use to see. Our eyes are tuned to those wavelengths only. Anything outside that wavelength we cannot physically see, we may be aware of by other ways. But of course light comes into our eyes and enables us to see. I will, however, mention one device in the visible light region, which is a very important device, and it's called a laser. Laser stands for light amplification by stimulated emission of radiation, which sounds a bit of a mouthful, but you just take LASER, and that's where you get it from. What you find is that a laser emits light which has the following qualities. Firstly, it's of a single colour, so it's what's called monochromatic. You'll often find red light lasers. Secondly, it is all what's called in phase. All the waves are radiating or oscillating in phase. Thirdly, it's often very intense. And fourthly, there's a very sharp beam. If you shine a torch, here's my torch, you tend to get a very wide beam of light. But if you have a laser, you will get a pencil thin beam of light. So all the intensity and all the energy is in that beam. And incidentally, you can encode signals within it. Exactly how it works I've described in my videos for A-level, so you'll have to wait till then. But one of the uses of a laser is in reading a CD. A compact disc has what looks like a flat surface, but in fact it has a series of notches in it. They actually have a particular name. The lower level is called a pit, the higher level is called the land. I suppose because it equates to ordinary land and then you fall down a pit. And what the laser is doing is pointing downwards, sending a beam of light down and up again, and timing how long it takes to go down and up again, so is able to determine whether it's fallen into a pit or into a land, and it interprets that information into sound, digitized sound signals, which are then converted into the audio signals which are sent to a speaker, which you then hear. We've so far spoken about radio waves and microwaves and infrared and visible light of our electromagnetic spectrum. If we want to receive those waves, we will need some kind of receiver. In the case of visible light, we've got one built in. It's called an eye, and you'll notice that your eye is actually quite small. If you want to receive radio waves that might have a wavelength of 1500 meters, and you really want to gather all of that information, you might need a dish the size of Jodrell Bank near Manchester. Huge contraption which is receiving radio waves. Generally speaking, the bigger the wave, the longer the wavelength, the bigger the aerial or the receiver that you need to receive it. Now, of course, we didn't used to receive radio waves when we got long wave off of our radios. We didn't have a great big receiver the size of Jodrell Bank. As often as not, all we had was a bit of wire dangling in the air. But that's part of the reason why the transmission and, or rather the reception, wasn't quite as good. But if you look out into space and you're trying to pick up radio waves, then you need a big receiver to receive them. So now we move to the next region, which is the ultraviolet region, where the wavelength is about 10 to the minus 8 meters, so it's getting even shorter. Your eyes cannot see ultraviolet, but ultraviolet is beginning to get into the dangerous region. We can have ultraviolet from the sun, which will give you a suntan, but if you're not careful will give you sunburn. So you really do need to protect yourself from ultraviolet from the sun. People do still sit under ultraviolet lamps or a tan that they don't have to sit out in the sun to get. These actually are probably not good things to sit under because they do have health issues. If you want a tan, by far the best way of doing it is to put on a fake tan. You know, one of these things you can buy from the shops and spray on. That's if you want a fake tan, of course. You may also have seen ultraviolet light used at a pantomime. If you've ever been to a pantomime and watched the stage show, quite often during the pantomime you'll see the ghosts dance, and the lights, all the lights of the theatre will go off, and they will have an ultraviolet light somewhere. And what that ultraviolet light does is it reflects off of certain materials and makes them glow or fluoresce. So you will often see ghosts in bright whites, bright yellows, bright greens, bright reds prancing around the stage, but you can't see the people who are in essentially black costumes underneath it all, because the ultraviolet light is only working on this fluorescent material and making it glow. And that's done by ultraviolet. Then we move up the scale even further to X-rays, where the wavelength is 10 to the minus 10 meters. And now we're getting very dangerous. These have to be used carefully. Of course, they do have very valuable uses. like medical imaging. They can tell whether you've broken your leg. Airport security, they can tell whether there's a gun in a case that's locked that's going through the security scanner. And then we get to gamma rays, where the wavelength is even shorter, 10 to the minus 12 meters, very high frequency, very high energy, very dangerous, but they can be used, for example, in other forms of medical treatment. X-rays are produced when high energy electrons strike something like tungsten, and that emits X-rays for reasons you'll find when you get to A-level. Gamma rays are the products generally of nuclear reactions. So if we now review the safety going from the right-hand end of the spectrum to the left, radio waves, pretty much completely safe. Microwaves have the effect of heating water, so since a lot of your body is made of water, there is a risk that microwaves could start to heat you, which is why people are worried about prolonged use of mobile phones, because mobile phones use microwaves. So there's a risk that those microwaves could be microwaving your head, which is not good, though I have to say there is no conclusive evidence that that is the case. Then we move into infrared, which is hot, so you can actually burn yourself as a consequence of infrared. Then there is light, which in normal circumstances is fine, but you can blind yourself if you look, for example, at the sun for a prolonged period, or indeed even for a short period. Never look at the sun with your eyes. Always make sure you use a proper filter if you're going to do that. Ultraviolet is getting more dangerous still, can cause sunburn. X-rays and gamma rays actually damage the fabric of the cells of your body.